welcome everybody. My name is John-Daniel Trask, and I'm the co-founder and CEO of Raygun, and I'm joined today by Matt Byers, one of our legendary software engineers here at Raygun. Say hi.
Hey, I'm Matt. I work as an infrastructure engineer here at Raygun. I work mainly sort of in the Elasticsearch space, dealing with pretty big data. So one of the cool sides of my job.
And as I've got on the slide here, you know, I'm an old man. I can only talk the talk. Matt actually does all this amazing stuff. So he's going to be joining me today, and that he's going to run a lot of the demos, walk you through some of these things. I'm going to talk a little bit about performance in general terms. I do enjoy coding a bit on the side at home, but you know, the joke we have here at Raygun is, you know, the synonym for technical debt is the CEO's code. It's questionable at best. Anyway, we've done a few of these webinars. You can ask questions, I believe, through the Zoom interface. So if you've got anything that comes up, throw it in there. We probably will wait to the end to have a look at that, just because, you know, it's a bit of a fiddly interface, but do drop any questions in there as we go. This presentation should take about 45 minutes all up. There will be an offline version posted later, so if you've got to go for any reason partway through, keep an eye out. We will be making that available online. But we really appreciate everybody who's turned up today to have a chat with us. Cool. So I wanted to start off by talking about why do we care about performance at Raygun. So many of you will know we sell products that help people measure performance and improve software quality, but why would we care about making our software high performance? One thing is we process a lot of data. So in any usual hour, Raygun will process more than 100 million API calls to our service, and each of those calls can have more than 100K worth of data attached to that. So there is just a lot of data that's flowing through to us. And so we started doing a little bit of math around this, and you can kind of think of it this way, is that, you know, if it takes 100 milliseconds to process a message and we were getting 100 million per hour, that's 115 days of compute time that's required to process that data. While if it was 10 milliseconds, that's 11 compute days of time. So we spend a lot of time working on trying to ensure that our infrastructure is really performant, because that allows us to make sure that our products aren't wildly expensive for the sheer amount of data that comes in, and because that does cost us money. Also, having that sort of low cost to serve gives us the ability to do things like funnel money back into our own business to grow it without doing external funding, that sort of thing. So it gives us a bit of a competitive advantage. And lastly, as I put there in brackets, I think we can all acknowledge that no one likes slow systems, right? It's interesting. We track our Net Promoter Score, the happiness of our users. Some of you very well might have received those emails from me. And whenever we have some sort of issue that's affecting the performance of the web app, it's amazing to watch that number just start to drop off really quickly. I think people really underestimate the impact of having slow software. So that's kind of why we care about it. Keeps our customers happy, make sure our costs don't get crazy, means we don't have to charge the earth for what we're doing, and gives us a bit of an edge. That's Raygun's internal reason for caring about this stuff. The agenda today, I'm going to cover some performance thinking. Then Matt and I are going to kind of both jump into looking at issues and where you'll see them, in particular in .NET, while Raygun works with lots of different languages today. In particular, we wanted to look at the .NET side of things. I'll then dive a little bit into how computers actually work, which is always an interesting piece of this talk, because we're obviously all engineers of some degree, and we all think we know how computers work, but there's a lot of stuff we don't take advantage of. So I'll talk a wee bit to that. And then the really interesting meaty stuff in my mind is Matt will run us through a whole bunch of code examples in .NET and .NET Core, showing some of the cool stuff that's arriving there to help make your software faster. Cool. So I promise I'll stop talking soon and we'll get to the interesting bits. But I just wanted to talk a little bit about how you should probably be thinking about performance. We've already sort of discussed the idea that performance is a feature. But when you're looking at something, you need to be thinking, is this actually costing us users? So that can be quite difficult to measure at times, because we know that if something is slow, people will disengage. similar to what we do at Raygun when we canvass our users, we can see that they become unhappy if things get slow. But it's quite difficult to understand how many people aren't, say, buying your product or continuing to engage with your service just because it got slow. So measuring that can be difficult, but it's something to keep in mind. It's also useful in a way. I talk to a lot of engineers who kind of go, we do have these technical debt things. I wish we could spend the time making this software faster. And they'll sometimes forget that if they're trying to frame that back to the business, they really need to couch it in terms that the business cares about, like this is costing us users, this is upsetting our customers, this is ultimately costing us money, because the second point there is it costing us money? Well, there's two things. Costing us users will always be costing a business money. Users are typically how we're getting paid, right? But it goes beyond that as well. Like if you could be looking at it and saying, hey, well, we're using 30 servers to do something that actually maybe like if we spent 3 weeks doing some work, we could bring that down to 5 servers. What sort of cost saving is that? You obviously still need to keep in mind what's the cost overhead of you being on payroll and the software and the opportunity cost of what else you could be doing. But there can be money elsewhere in performance. I've often joke here sometimes when our AWS bill gets too big, I sort of think, what are we going to do about this? And usually it's a case of let's think harder about these problems. And some of the things that we walk through today are going to be examples of different coding techniques that we've brought to bear to try and reduce some of our server infrastructure costs. And lastly, when you are looking at performance things, you tend to want to do some measuring around where is the actual problem. And I see this a lot as well, which is folks guessing where there's an issue. And I'll give you a concrete example from Raygun, which is that we have a real user monitoring product. So that's tracking the load time that users experience. And when that data flows through our API, it gets queued for processing, and we have our RUM worker, right? And we have some absolutely colossal customers using that product. And we were sitting there going, man, this needs to go faster. There's so much more data that it needs to process. And of course, we looked at this and we thought, all right, well, it's touching databases nonstop throughout the critical path. Clearly, talking to another server is going to be a fairly big overhead in performance. And then when we sat down and actually profiled it, it turned out that part was negligible. We had a user agent parser, which parses the user agent string from our web customers. And that thing was gobbling up easily about 80% of the time. So we're typically, as human beings, not the best at guessing where these issues might lie. And so it helps to always measure. And we'll talk a little bit about some of the tools that you can use to do that. So a few things that we want to be thinking about in terms of performance. We want to be monitoring performance in production. It's always important to understand how the users actually experience it. It's really easy on developer machines that are highly powerful machines and typically only have one user using the application, that it seems like performance is fine. In complex scenarios where your code is executing in production with potentially thousands or even, for some of our customers, millions of concurrent users, being able to see that in production is really important. And that's obviously partly what we sell. I talk about the user experience. So I think there's been a shift in the market, an additive shift, if you will, from going from server monitoring in the past to wanting to include that real user part. And an example of that is that, say, an APM product, an application performance monitoring product that's tracking what the server's doing, might say, yeah, the server returned the web page in 800 milliseconds. And that sounds like a pretty fast response time. We're all happy with that. But as the industry's moved in the last sort of 10 years, 15 years, we've put so much more code on the front end in our JavaScript that it's not uncommon now when I'm helping our customers with their RUM data that they'll say, well, the server might have come back in 800 milliseconds, but the user then had to wait 4.5 seconds for the page to actually be ready to use because of all of this code. And there's not really any easy way to get visibility on what's the user experience looking like versus what the server's looking like. And that's where a RUM tool comes in. Matt will be firing up a profiler at some point, just giving a quick look at that for folks who haven't used a profiler to identify hotspots. And then lastly, we'll talk about building benchmark suites for keeping an eye on those hotspots over time and keeping them dampened down, really. So there are a few things we want to be covering today. So we'll jump from there to .NET performance smells. And so I've got an important note here, which is, again, why we want to track our software and understand where the issues lie is because it doesn't really matter if we have slow code if it's not on the critical path. If it's, a common one for this is, say, a service that might run daily on a server that's just rebuilding an index or something. If that takes 1 second or 1 hour, it might not really matter, so we don't really care. It's only when we've measured and found that this is on the critical user journey. So don't take what I'm about to go through as don't use these features at all. It's more just being mindful. So the first one's really easy, and that's link. One of the things I love about link is it's so easy to identify in code when you know you're looking at an area that's on a critical path. And obviously, link is a fantastic addition for developer productivity. You can sit there and string together one line that sorts, cuts, distincts, does whatever you want, groups by, crazy stuff that might have required hundreds of lines of code in the past. And that's really, really helpful. But because it's so generic, it's actually quite hard under the covers to optimize. And in a past life, before we built Raygun, we actually built an object relational mapper which had a link provider. I can tell you now, link providers are incredibly difficult to build and doubly difficult to then try and make it so it actually does optimize for the way a human being would sort of go, well, surely this would generate this sort of output. So be mindful that it's never going to be that optimal. And as an aside to that, there are actually open source libraries that people have built for more efficient versions of link. So ones that will try and reduce memory allocations or operate more efficiently than the default link providers. And to give you an idea, I'd like to back things up with facts. Let's take a look at this little bit of code here. So what this is doing is it's finding a section within a dictionary, and then it's checking if those sections contain that character, and then they're selecting back the value from that dictionary and putting it in a list. All right. This is a link version of this sort of expression, and we'll jump to a version that's not using link, which oddly, in this case, I actually find this one a little bit easier to read than the link version. And we kind of want to see what's the performance difference between these two. Now, for some of you, you'll realize that part of the question comes down to what's the range, because we need to know how many things we're checking. And we do actually have the benchmarks around that, I think, somewhere. But it was a reasonable range of a couple of thousand at least. So let's jump over to the results. So this was the code when we were running it through link, and it took just shy of 4 seconds to execute, right? How much faster do we think it is if we don't use link, Matt? And just pretend that you don't know what the next slide says.
Surely it can't be any more than 2 times as fast, right?
It's actually, it's a little bit faster.
Just a little bit?
Just a little bit. It's a full 474 times faster to not use link. Right? Because what's happening behind there is it's having to pass expression trees and look at these things and allocate temporary data and chain these things together and do all sorts of heavy work. So we're down to 8 milliseconds. Again, though, we really wouldn't care about this if this was, say, a link query, link execution on like a background process that really didn't matter and the computer was otherwise not doing a heck of a lot. But this is really cool because it does mean if you're looking at some code and you know it's on the critical path, you can just pretty much eyeball and see that there's some link code in there and be like, right, well, if I start by taking that out, what are we going to see here? This next one's a little bit aimed probably more at junior engineers, people coming into the industry. Exceptions. So I know the exceptions really should be exceptional. It's kind of built into the name, right? And by that, it means that it should throw when there's an error, something happened that shouldn't have happened. But what I see occasionally is people generating exceptions to try and sort of pass up or pass the return further up the stack. And years ago, I remember we actually bought this website for marketing reasons, and it was written in .NET. And it was kind of crazy because the code was not good. In fact, when people saved it, actually it threw a unsuccessful save exception as a method of notifying further up the stack. Now that's an extreme example, but one of the reasons we do want to be mindful of exceptions is not just, hey, exceptions are probably bad, it's that exceptions are quite costly. So this was a case, I think from memory, of generating about 10,000 exceptions, and I was doing it in a simple flow control situation where this took about 8 seconds under this loop, where if I just used normal stuff, it was a lot faster. The reason for this is an exception will typically try and, it kind of has to almost stop the world. It collects stack trace information. It does all sorts of weird and wacky things inside of the runtime to capture this metadata, because it should be an exceptional error type state. And if you're just passing things around simply, you really don't want to incur that overhead in there. So just include that one nice and quickly for those of you who are looking at exceptions. So there are a couple of quick smells. How do we go and find some additional smells? So under this case, I'm going to get Matt to fire up .trace on his machine and give you a quick look at using a profiler in here. So just bear with us 1 second. I think you just escape, fire this up.
Cool. So what we tend to use here at Raygun is
.trace.
.trace.
So if we fire that up from there, just type in .trace. Oh, you run it from the. As an aside, if you use any of the JetBrains tools, I highly recommend going and grabbing this JetBrains toolbox that's sitting in the side here, because it'll tell you about the updates. You can click and have it automatically update those. It's just a super handy addition to your developer toolbox. I don't know where I'd be without it these days. Given that I don't code a heck of a lot, it's useful because usually there are updates to the IDEs and tools every time I actually find some time to sit down and do something, which is handy. So have you got an existing profile kicking around?
Yeah, so the cool thing about .trace is it actually saves all your snapshots from previous runs you've done. And in terms of actually running them, you can attach to an already running app, you can attach to an IIS instance, or you can just spin up a new executable within .trace itself. So I'll go and find one of my previous runs I've got here. Yeah, let's just take this one.
Cool, good guess. W3WP. Excellent. The other thing too, while we're demonstrating JetBrains .trace today, there are a bunch of profilers. Visual Studio has a nice basic one built in these days, and there's also profilers from folks like Redgate. Really comes down to just whatever you're comfortable with in terms of the different tooling. People here at Raygun use a mixture of them. But anyway, I'll let you demonstrate what you're looking at here.
Cool. So this is a trace from a usage counting service within our system. So as you can see at the top level, this async request here is taking about 3.8 seconds. And what you can do is you can just expand out each section, and you can just go dive deeper and deeper down the tree to see what sort of is the main performance area in this this trace.
Where the time's going.
So as we go down further and further, it starts splitting out and the tree starts to sort of expand. And we're seeing here that most of our time seems to be coming from this get from database call. And we're going further in and we're seeing that pretty much all of the time is taken up by MySQL. So in this case, if you wanted to sort of improve this, you could maybe think about not going to MySQL so often, maybe going to some sort of transient data store like Redis and then flushing out of Redis every so often. But it's really cool just to be able to dive in and sort of see at a really high level like what each method call is taking in terms of time and overhead.
Yeah, and you see you've got the code there on the side now. Because Matt's opened up an older trace, the PDB file, which is the debug symbols for your .NET code, is now out of date because every time you compile, it generates a new PDB. But there are various different profiling modes as well that you can use with these tools, which will allow you to get down to line by line. What's the time that's going on in here? and track exactly where things went, which goes back to that earlier point I was making about not just assuming you know where the performance would be going, because you'll often find you're surprised when you actually run this stuff through a profiler. .trace found really easy to get up and running. You can either attach it to an existing .NET process, or you can have it start one. So for example, if you have a console application, you can point it just at that, click run, and it'll capture the data for you. So really good on your developer machine. But the problem arises, what are you going to do when you aren't on your developer machine, right? So what happens when we actually know we have an issue in production, but we don't have that issue seemingly appearing in our local development environment? And this goes back to the issues that we see with just the complexity of a load environment in production. So what we're going to look at here is an APM product. I'm going to flip that around. This guy's, it's probably not much point in jumping back in here. But we're going to show you an APM product, which is a shameless plug for our own one, but really any APM product is useful for understanding this. We just think the Raygun one's probably a bit better. So what we'll do is we'll jump in here. I'll get Matt to just open up his account. And so by way of background, Raygun, we have crash reporting, real user monitoring, and APM product. The APM product is available for .NET and .NET Core. We released this late last year. So maybe open up the Mindscape site. And so what an APM product is actually doing is it's kind of like running a profiler in your production environment. And we obviously do a whole lot of work to try and make sure that that doesn't have any real impact on the execution of the code itself. So when you're running profilers on your dev machine, you'll notice that it slows things down a lot. So we have to put a lot of work into making sure we don't slow down production code. And so what we've got here is we've got a website. It's our old Mindscape website. So this is just really it's a brochureware site that built in ASP.NET MVC4, I think. And you can see in here, we've got things like an AppDex score, which is a computed overall health score. But we can see here the execution time for each of the web requests or transactions, if you will. We also make sure that we show you the outliers. So P99 means like if we were to line up everybody on their performance and we said, who are the 1%, like that 99th percentile way through that collection of people, what was their load time? So you can kind of see this here. We can see that the worst people were experiencing 2.6 seconds or longer wait times, while 50% of people or more were getting 3 milliseconds or less. It's a pretty low traffic in the website, so it's probably more of a cache hit type scenario for the medians there, but it gives you that idea of a distribution. But you can see here, look at this, the request breakdown, what was going on. So we can also tell you where the time went by saying, okay, well, there wasn't really any overhead in the API calls, but there was a huge hit in terms of the method execution. So what was going on in there? And you can see it looks like it was a total outage of this website at that time. You can do all sorts of things in here, like drill in. We might want to go, okay, what was actually in that spike? And that's pivoted all the data around you. And we might go, okay, let's sort this. We might go and have a look at this page here, this request. Now this looks like a URL, but it's actually going to take us to all of the data for this URL for how many requests within that custom time frame we've selected. I mentioned it's a pretty low trafficked site these days, so there's only one request in that time period. We can actually go down and look at that particular performance trace right here. So clearly there's a bit bugged, I've seen this before. But what we're looking at is a flame chart. So this is a different version of what we were just seeing inside of .trace for this exact request that this user had made to this URL. And what we can do here is we can actually see that there's database queries that are firing. We can see the actual queries themselves, what they came through as. And if we just click that there, if we click on this, it actually also integrates directly in with your source control. So just like in .trace, we can start to see, wait, what was this code actually doing? Where is the issue? Oh, the Tolson hack. Right, apparently the code in this website, you know, if it's got more than 17 pages, it's only got 17 pages. Interesting. We can drill in and zoom around on this thing all we want. We can see a summary of where the time has all gone between database queries, the code, known libraries. We can also do cool stuff in here, like go and look for issues. So we're automatically picking up when we have N+1 database queries and things like that. Not going to kind of keep going too much on Raygun APM, but this is giving you that idea of what the heck is actually going on in my production environment that might be making things slow for my users. So we want to make sure that we're assuming nothing, we're actually measuring everything and understanding what's going on. Cool, so I'll jump over here. So the third tool, benchmark.net. So I'm gonna pass over to Matt and he's gonna show you this. This is a very, very cool tool. It's really one of the most exciting things I think I've seen in .NET land in the last few years.
Cool. So benchmark.net allows you to sort of get a profiling of a individual method call or a smaller piece of execution. It takes quite a while to run, so you don't be wanting to benchmark big areas of code, otherwise you'll be sitting there for ages, because under the hood it actually does all the statistical analysis and runs it over and over again, and sort of getting you that the deviation and all those sorts of statistical numbers. So what you with benchmark.net, it just installs via a basic NuGet package. Just searching, let's see if we can bring that up, just give you an example. So just benchmark.net, install as a NuGet package. Now, in terms of actually using this thing, what you do is you wrap a certain piece of code in a benchmark statement. So let's go to this example here. Don't worry about that. Benchmark like this, and that basically is saying that this area of code is one iteration of this benchmark. And each one of these will produce a new result in your result set. So global setup, this is another attribute that you can use. This basically says that this is going to be run before each benchmark iteration. So you can do some basic setup and things like that in here. In this case, it's allocating an array that will be used in both of these benchmarks to perform the different tests. Diagnoses are another concept which are good to know about. Memory diagnoser, in this case, just gives you a look into the heap and the garbage collection cycles, so you can see what is being allocated and unallocated in that, that benchmark run. Params are another good one. Allows you to run a new iteration of each benchmark to basically say run this benchmark with a value of this on this property. So characters count, we have 100 in one test run and 10,000 in the next. Baseline is another good attribute you can use, which gives you another section of your results, which says how much off the baseline the other tests were, basically. Gives you a percentage from the baseline result. And yeah, that's pretty much it. We'll, I'll show you a basic output of benchmark.net. Don't need to spoil any results, but you can just see the method name, any params that it was run with, the mean, timing, and error and standard deviation. This is what I was meaning with the statistical side of things.
It's also quite cool because of all the statistical work that they do, they'll also remove any crazy outliers. So for example, if you're running on your machine, you know, you never know what some background process might do. And so something could happen that actually chews up a whole bunch of compute time briefly and makes one of the test runs, you know, statistically anomalous. And so they'll actually highlight that that occurred and remove that from the set. And what Matt's done here is he's scrolled this up to kind of show you some of the output when this executes. So you can see, like, they figure out, okay, we want to actually JIT the code, because obviously in .NET, when we compile to the intermediate language. And then when it runs, the just-in-time, the JIT environment will actually compile that code down to the native stuff for the platform and execute that. So we don't necessarily want to be including the JIT time and how long our code takes to execute. We want to understand at the low level. as Matt kind of touched on at the beginning, though, this is really designed for micro benchmarks. If something was going to take like 10 minutes to execute, I would hazard a guess that the defaults, at least in benchmark.net, would probably take about a day to run that to get you the data. So you really want to be looking at small little bits of code that are really performance sensitive. What's really cool as well about benchmark.net, other than everything that we've already covered, is it's becoming a real de facto standard in the .NET community for measuring performance. So if you read blog posts from Microsoft on improvements that are coming into .NET Core, or you look at the PRs for .NET Core, they'll often have benchmark.net output as the sort of proof that things are getting better and how they went from A to B in there. So really, really powerful tool, completely free. The code's all on GitHub. The folks who have worked on it absolutely doing God's work for the .NET community, which is really cool. All right, jump back to some of the other performance bits and pieces.
Yeah, what next?
So I was going to start talking about how computers work. So let's run that up, which every single time. I bet we'll get to the end of this presentation.
It'll finally work. All
of the questions will be saying, you need to tick this box, and it would have just done it for you.
Yeah.
Fine. So anyway. So I want to talk about how computers work, because oftentimes these days, and it's an amazing time to be a software developer, right? We're working at pretty high level, and we've touched in this talk about things like Link and how we can get a lot done very easily. But I wanted to dive under the hood and actually examine, how does the hardware work? What's going on here? And so I wanted to start by talking about memory. And as most folks will be aware, we know that when something's in memory, goes really fast, and that's where we got all these like in-memory databases and things like that to help stuff be fast. It's been kind of interesting over those years since we started to see the in-memory stuff come along, because we've seen stuff like NVMe drives arrive with like 3 GB per second read and write times, which is kind of crazy. That's getting pretty fast. But I wanted to dig in on memory, because we talk about how it's fast, but kind of in actuality, it's not actually that fast, right? And so what I've got in this chart is the general time it takes to access data from various places. So we've got RAM over here on the side. So that's taking about 100 nanoseconds to fetch some data, which, I'll be honest, 100 nanoseconds, that sounds pretty fast. But then on the CPU, we have these additional caches. And so you'll typically, and if you read the box on your CPU or look it up online, you'll see how much is available in terms of level 1 cache, level 2, and some have level 3 and even level 4 caches. And they typically are just taking data to be a lot closer to the actual execution engine on your CPU. So L1 cache, effectively very similar to using direct registers that are on the CPU. What you'll find is that you'll have an L1 cache, say, per core. You might have I'm going to get this slightly wrong, but things like the L2 cache will tend to kind of be available to maybe 2 of the cores, and then L3 might be available to the whole chip, and they sort of trickle down. They all have different operating modes that are in there. The other thing to be mindful of is these days, you might have 32 gigs of RAM. You might only have, say, 64K of L1 cache, and typically on server grade CPUs, you might start seeing things like 64 megabytes of, say, L3 cache. So they're definitely smaller. You're not going to, no one's really about to launch an L1 in-memory database. Be pretty small. But they are terrifically quick, right? Crazy quick. Effectively, we can do things 200 times faster if we're doing it from the L1 cache. But of course, we still have to get the data from RAM to the L1 cache. In fact, we probably have to get the data, at least we're generating it in memory, from the hard disk to the RAM to the cache. So why is this important? Well, firstly, because memory is kind of slow by comparison, we don't want to allocate much memory. We want to minimize that. And you'll see this a lot if you've been following along with the evolution of .NET Core. A lot of work has been going into reducing memory allocations. And you'd think, well, if it's quick, why is it that big a deal? It's because it does stack up. And we'll also dig into this in more as we go along. And there have been people in the community like Ben Adams who, kind of these days think of as the memory allocation hunter. He just goes out and tries to remove everything from ever allocating memory, which is pretty hardcore to see in his pull requests. But there are some areas where we want to think about memory allocation, like, and I've got them listed as smells here: JSON data, XML data, regexes, anything that's using strings. These things tend to be magnets for allocating memory like you wouldn't believe. And then within .NET specifically, you've got this thing called the large object heap. The way that this works is the idea that when an allocation is large enough, it doesn't go on the normal heap within .NET. It actually goes on the special heap that says, I'm for really big objects, right? And they get treated quite differently by the garbage collector. It's also typically quite slow to work with, and we'll cover on why that is shortly. But here was a cool little thing I wanted to show around memory and why it helps to know how the CPU actually works. Let's look at this code here. I've got two things that are effectively doing the exact same thing. Don't forget to track your time for that. What's the difference? The difference in this code is how we access this map. Are we going breadth first or depth first? Effectively, it's just a two-dimensional array, right? But it's otherwise doing exactly the same thing. Oh, there we go. If we go and have a look at the performance of this, and I've tried to keep this a bit of a mystery, this is the time it took. So it was about half a second for the execution here when we went NI. What do you reckon for IN? I see you staring right at the other screen, so you know, so I'm just going to say 5 times faster. Effectively the same thing occurring. But why is that? Like, you know, it fetches stuff from memory, it does some work, you know, counts it up. This should be kind of the same thing, right? Well, the way that CPUs actually work is that when we request some data, we don't actually just tend to read in only the piece of data that we've requested from RAM. Things in there are managed in sort of pages and blocks and all that sort of good stuff. And this here is representing the cache on the CPU, and this is representing our RAM. So what's happening is it's coming through here and it's going, actually, I need this, and it's fetching in a little bit more than what you'd think it would be fetching and storing that on the CPU. The problem is if we are actually reading this where we might be jumping in the wrong order, we could be jumping from where that dark rectangle is to maybe like 6 or 7 down the stack here, at which point we're actually we're requiring our CPU to throw away this extra data that it fetched in there, right? And so thinking about how memory actually works and how that data gets in there allows us to really take full advantage of the performance of things like the on CPU caches to eke out a little bit more performance for our users and ourselves in there. But why should I even care? I mean, memory's still fast. We're talking half a nanosecond versus 100 nanoseconds. I mentioned we need to think about all of these things that are bleeding memory, right? They're using heaps of memory. So we've already covered that memory is actually pretty slow by comparison. One of the things a lot of people don't know is that when .NET allocates memory, it'll actually go through and clear the existing memory. I haven't really dug into the exact reason for why. I'm going to just assume that this is because it has to set up the memory for how it lays it down, and maybe also for security reasons to ensure that you couldn't accidentally read into something that was there. But when you've got 2 cycles per byte, from memory, I think that came out at something like 16 milliseconds would be chewed up if you allocated, I think it was a 16 megabyte block or something like that. So you're actually eating a bunch of time even before you can start to allocate. And because we're not having to do explicit memory management in an environment like .NET, we often are creating allocations without even realizing that we're doing that. So these ones are really obvious, but this is sort of stuff that I see a lot. And I did the same when I was a junior programmer. You know, I might be doing something like this because I want to count up all of the sections outside of the commas. But actually the split, because strings are immutable, they cannot be mutated, this is going to actually allocate a new string for every block that's in there. And use up a whole bunch of memory. Similarly, something like this, where we're replacing, even if there was only one space, this will actually have to reallocate the entire string. So if that string was maybe like, who knows, 30K, 100K, take, for example, the data that Raygun receives, we might have 128K error message come through. If we were to do something like this, we can quickly be allocating many, many megabytes of memory, which is kind of crazy. So how do we get around this, Matt? What have you got for us? Well, strings seem scary to me at this point.
Strings seem very bad at this point. So one of the sort of key performance improvements that we saw with .NET Core, it was the introduction of span. The span's a new type that has been introduced, and effectively what it allows you to do is work with or have direct memory access to any sort of contiguous memory blocks in a sort of type and memory safe way. Now the efficiency is gained in spans by the fact that it doesn't use allocations. So you can access a string, you can go to any partner string with the slice function, and you won't see allocations like you would see with the string.substring function, for instance. Now there are some sort of limitations to span at the moment, because it allows you to access any kind of memory, which includes managed and unmanaged memory. You can see limitations like the fact that it can't be put on the heap. So it's a stack-only type. And because it's a stack-only type, you get some sort of little gotchas, I guess. One being that you can't store it as a field, or you can't store a span as a field on a class, because that class could go onto the heap, or go into the heap, I mean. And other sort of annoyances like it can't be used as a parameter for an async method. There's some reasons behind this to do with the async state machine that is created with async methods. And because it's a stack-only type, you also are unable to share it across threads. So it's a good thing and a bad thing. It means it's thread safe by nature. But yes, so what we wanted to do with span was give a quick little example as to how, or the type of performance improvement you could see with using this over so string.substring, for instance. So here, do you want to
yeah, well, I was just going to say, so you ran this through benchmark.net.
Yep.
As a way of doing this measurement, but we'll and I think, are you going to plan to post the code along with this somewhere? Maybe we get a blog post up afterwards as well, so folks can actually run this and see it for themselves. But yeah, cool. So substring with, I did this test with 100 and 1,000 characters. Oh, 10, was it 1,000? 1,000 characters, yep. So where did we end up?
And so this is sort of taking 7 nanoseconds, and this one's
millisecond. Oh, nanoseconds, yep, cool.
And with slice, both pretty much minimal or nothing. 1.1 nanoseconds, or around 670 times faster in this case.
It's pretty quick. So yeah, effectively not having to touch the memory to actually do an allocation, you start to realize that's pretty much where all the time is actually going with these things, is because we're touching memory, and all of this stuff is often happening either inside of libraries we're using, side effects of code we're writing, all of that sort of stuff. So yeah, you're going to show the code a little bit?
Yeah, so I was just going to do a quick sort of demo of what the test was actually doing.
That's right there.
Oh, already on. So really basic example, literally substring getting from 0 to half the length of that string. And the span version is just, this is another cool thing with span, is you can literally just cast a string to a span and then access it that way, and then you save yourself those allocations, literally just with pretty much one more method call. So ran that through benchmark.net, and as you can see actually on that, I've used the memory diagnoser just because we want to get a little bit more of a deep dive into those sort of memory allocations, so we can see that how this thing is gaining that efficiency. So let's just find it in this big, horrible output. This is why benchmark.net takes so long to run, as an aside.
Yeah.
And what order was it in? Let's check that in the program. First one.
Cool.
Cool. Just bear with me. And here we go. So this is the parameterization of benchmark.net. You can see that this is the 100 character run, and this is the 10,000. So what's 10,000? The slide was a bit wrong there. You can see the mean times and the actual values of the performance improvement we saw there.
What's quite cool here as well, you've got the memory diagnoser on, so that's why we're getting these extra columns in here for the number of the generation of the memory allocation per instruction, that sort of thing, which we're not actually seeing with anything, except you can see here we're getting the Gen 0, sorry, is only showing up on the substring thing, indicating we have allocations that are occurring under the substring one, while the slice actually isn't generating any memory allocations at all. Which is pretty cool to see. And that was with just putting that attribute on that says memory diagnoser. I think you put it on the class, so it applied to all of the tests that were in there.
Yep.
Which is pretty neat.
And the other cool thing you can see is that the time doesn't scale at all with the with span. It's 1.2 nanoseconds for both 100 and 10,000 characters, which is pretty cool. And you can actually see the allocation. It's kind of gone and truncated around 128 bytes for the 100 characters on string.substring, 1,000 bytes for 10,000 bytes for substring, and then slice nothing and slice nothing. So you can really see where that performance improvement comes from and saving those memory allocations there.
Cool. I'm a bit mindful of time, folks, so we'll try and accelerate a little bit here. We were aiming for that 45-minute thing, so I'll speed up on this one. It's never going to do it, Matt.
I thought it was going to work.
Cool. So let's go and talk about the large object heap. Now it's important, so I'm not really giving it a whole lot of. I'm not really laying the smack down on it. It's just something to be mindful of. So at the moment, and this stuff is always subject to change as our industry moves on, but basically any object that's going to exceed 85K is going to go on the large object heap that I mentioned earlier. It does not currently defragment or compact itself, meaning that, and I'll show you in a demo shortly, it won't shift things around to keep space free. You can, however, send a signal to the large object heap or to the garbage collector that it should do some compacting, but what it's going to do is it's going to stop effectively the execution while it does that. So that means if you've got a real-time piece of code that can't afford to stop, you don't really want to signal this. Microsoft have included in their documentation to not rely on the fact that this doesn't happen automatically and that it may change in future. There's the bit that I was talking about before, 170,000 clock cycles just to do the memory clearing on an 85K object. So you can kind of see again why that's taking a while, and then there's that 16 milliseconds of clearing alone on a 16 megabyte object. Which is pretty insane in there. So why would we care about needing to compact memory or worry about the large object heap and things like that? The reason is this. So I've got a very simple, very old computer with 16 megabytes of memory, and I allocate 16 1 megabyte objects with no memory, and then I clear half those objects. The GC goes through and cleans them up. Now I need to allocate 5 megabytes of memory, and boom, I can't. I get an out of memory exception, even though technically I have the available memory, because the way that we have to lay objects out is that they have to be in contiguous blocks. So this is where you can have, say, and we have to think a little bit about this when it comes to like our background workers that are processing our customer data, because they're typically all quite large objects. How we don't want to end up Swiss cheesing the memory too much and ending up where we can't allocate objects, even though there's a fair bit of memory available. So that's just something to keep in mind as well about why we would like to try to avoid memory allocations, especially if they're going to end up on that large object heap, because life gets hard there. Talked about JSON being a bit of a code smell, because obviously JSON strings, and you know, I always love people saying, oh, it's great because JSON's so human readable, it's fantastic. It's like, yeah, it kind of comes at a bit of a cost. and you can see extreme things like Google introducing protocol buffers and things like that try to use binary formats to be more efficient at their scale. That's important. And I just want to be clear here, I'm not having a go at JSON.NET here, but it's also not the world's most performant JSON library either. And so the .NET Core team is working to improve the JSON performance in .NET. And they've actually hired James Newton-King, who built JSON.NET. So he's helping, I believe, work on parts of that. And so in .NET Core, they've introduced this new thing called JSON document, which is not part of JSON.NET. It's built into the framework. I'm going to let Matt take it away with his demos.
The JSON document is cool as it's built on .NET Core. We sort of see that performance boost coming in from spans because JSON document is highly built on top of spans. So you save on all those allocations. So we've built another demo in Benchmark for this one. And JSON demo. So we use JSON format for our crash reporting processing. So I've kind of got a real world example here, and I've sent in a dummy crash reporting payload as our sort of test setup here. And I've done 2 tests, basically to pull out this one property from a parsed crash reporting payload, which is the request query string, and then the SKU in this case. And we've done that with JSON .NET, and then we've done it with JSON document. JSON.NET syntax is sort of deserialized into a dynamic with that payload, and then we end up with a dynamic where we can just sort of pull the properties off as we want. A little bit different on the JSON document side. You've kind of got this typed model where you kind of move your way down the tree by getting properties based on their string names. One difference we've got to kind of illustrate here is that JSON convert or JSON.NET can serialize into an object model, whereas JSON document can't yet, and they plan to add that in later JSON document support. So with the test on that one, it's the second one. I'll put these in order, that's good.
It's like you had a plan the whole time.
Exactly. So we're seeing 229 microseconds on JSON.NET as opposed to 73 to pull that one property out on JSON document. And you can imagine if you're doing lots of those over the...
well, like you say, we're dealing with more than 100 million an hour.
And just to pull out one property of those, we're taking sort of 229 microseconds. You think trying to parse that whole document into a model.
Yep.
And we can actually see the efficiency that Span's giving us here in the allocated memory. So we've used the memory diagnoser from benchmark.net on this one again. And you see 128 kilobytes of memory allocated for JSON.NET and 104 bytes for JSON document. So we're seeing the memory allocation of that one string that we pulled out for JSON document, whereas the whole model is being parsed for JSON.NET and allocated into objects.
Yeah, cool. Let's jump back in since we're
running long.
That's all right. I'll flip this around.
Once more.
Cool. So I wanted to talk a little bit about the CPU themselves. So one of the things we don't think about a lot these days is the actual instructions that a CPU has. This was talked about, I feel like, a little bit more back in the 90s when there was the battle between will RISC architectures beat CISC architectures and what's going to happen here. And the way I sort of describe it is that you can kind of think of your CPU as like a calculator, right? And the plus button is one instruction, the subtract is another instruction. But the fact of the matter is that your CPU actually has hundreds of different instructions, but you don't tend to think about them because you're working in these high-level languages, right? You don't have to think, oh, goodness, does the CPU have this? And that's been nice, but it also means we're leaving performance on the table. So, for example, when we tell a CPU what to do, this is kind of the assembly code version of saying, right, we would like to add 4 to the value of this register ESP, which is going to be a high performance register in that sort of half nanosecond time range. But you might start to wonder, well, what other instructions are there other than add and moving stuff around between memory and whatnot in there? And as you can see on the slide here, there's actually quite a lot of extensions to the core CPU instruction set. So the older ones amongst us here will remember things like MMX turning up in the 90s. That arrived around the time I think the internet started becoming popular. So Intel added these multimedia instruction set, and it had things to accelerate things like the JPEG decoding type algorithms. And then AMD followed up with 3D Now, another case where 3D didn't really matter, but let's stick it on there anyway. And this has just kind of evolved, and CPUs now actually have this whole long list of different things that they can support. And we're going to talk a little bit today, in particular, about SSE2 and AVX2. There are a whole different breeds of these as well that are out there, and not all CPUs are the same. So even when you grab the code for this afterwards, you might find that your CPU doesn't, say, support AVX2 or something like that. And there's also newer ones like AVX512 that are out there that are really only on certain server class CPUs and stuff like that these days. So it gets really interesting, though, to start wondering, what is my CPU actually capable of? But like I say, today we're going to focus on SIMD instructions. So SSE2 and AVX2 are part of a single instructions, multiple data. And so what this means is, if you already know that a CPU kind of has a clock cycle, right? Let's say 4 gigahertz, right? So 4 billion instructions per second. Let's say we were adding numbers together. We could add 4 billion numbers, in a second. But what if we could do more of those per clock cycle? And in this case, SSE2 is going to allow us to do 4 at a time. So suddenly we're getting the equivalent of like 16 gigahertz worth of throughput. Or in AVX2 land, we can do 8 per clock cycle, which is going to take us up to 32 gigahertz worth of throughput. So you can kind of see here, if you've got really heavy number-based stuff, you can get some incredible performance out of these things. Makes me a little bit sad remembering back to my old 25 megahertz CPU, Now, whoopsie, went forward. One of the things here is that we're going to be demoing this with .NET Core. .NET Core is doing some amazing stuff with exposing these sorts of instructions to you as an engineer. However, you can use the system.numerics library on NuGet with full framework. You do have to use the newest version of the jitter, though, to have that work, or else the performance will actually be worse. And system.numerics was kind of felt a bit like it was a playground, an experimental package back in the day, while in .NET Core it's sort of built into the foundations and exposing a lot more of these capabilities that are in there. I do note that if you kind of really get into this sort of stuff, you may even want to start looking at general purpose GPU programming, which takes, rather than saying, hey, we could do 4 things at once or 8 things at once, maybe we want to do like 10,000 things at once. Which can be quite interesting as well. So we're going to jump to a demo. I'm going to get Matt to do this as well for me. It's worth noting that all of this stuff in .NET Core is included in what's called the intrinsics namespace. So you see up the top there, system.runtime.intrinsics, and there's x86 in there because .NET, of course, can run almost anywhere. So you might have ARM and intrinsics and capabilities on your CPUs as well. So, all right, Matt, let's speed through this one.
Yep, so just speed this up a bit. This is just a basic test. We've got an array of integers, and we are checking basically if the array is sorted. So we've got an example here for just the regular or the baseline method of sorting. Then we've got an SSE version and an AVX version. So you can see here that these are using vectors under the hood. So we've got 128-bit vectors for SSE and 256-bit vectors for AVX, and that shows you the difference in size. So SIMD is also known as vectorization to some people, and it allows you basically to apply that same operation to multiple parts of an array at once. So 256, we can fit 8 integers into that, so we're comparing 8 integers at once, which gives us a nice performance boost, we'll see. So jump to the results here. Speed down here. This one last, anyway. Cool. So with an array size of, what do we got here? 1 million ints. Mean time for regular is sorted implementation, we're seeing sort of 1,000 microseconds. SSE, we're getting a nice bump up to 379, and AVX, another nice jump to 240 microseconds. So you're getting some nice performance wins there just by changing your implementation, and the functionality is all still staying the same.
Yeah, effectively what you're doing is just squeezing out more work per clock cycle with this one. So we haven't worried about looking at the memory allocations on this one either, because it's kind of irrelevant here. But like I say, what's really neat is starting to ask yourself, what else can my CPU do? And there's some really amazing blog posts that are starting to show up from folks that are doing some really deep performance improvements using different parts of the intrinsics namespace. And there's a whole lot more around that coming as .NET Core 3 continues to grind through its preview stages and head towards RTM. I will speed this up. I just wanted to talk about how if you move to .NET Core, you're just going to get performance wins in general. So a lot of the stuff we've been talking about with spans and intrinsics and all of this good, reducing memory allocations has kind of been baked into .NET Core when they've rebuilt this from the ground up. So this is a little bit of old data from a Microsoft blog post. I think it was from when .NET Core 2.0 shipped, and they talked about the performance improvements here. I think the overhead in this was around, it might have been milliseconds to do certain things. There is a post linked at the end of this presentation, but you can see overall performance improvements have come through across the board. So you may even find just moving to .NET Core makes your code faster by default. Lastly, a couple of bragging right things that the Microsoft folks have well earned. The last round of the Tech and Power benchmarks, which is a global benchmarking I guess you'd say, like, it's what everybody's trying to win on in terms of their performance of their web frameworks. And you can see here, ASP Core is now sitting right up there at number 7. This was for one of their particular tests. And I believe that my understanding is that all of these frameworks are pretty much getting to the point where they're actually just network bound. They can't get more data through. But if you look at this, I believe ASP.NET Core is probably the most broadly adopted commonplace programming environment in here out of the top 7. Some of these are a little bit more sort of academic proof of concept, high performance things that you may not actually use yourself. So it's really exciting to see that in there. And they're only 0.3% slower than the fastest framework out there. So even though it's a fully managed environment, you're definitely able to get terrific performance out of .NET Core these days. And like I say, that isn't even with .NET Core 3, which Microsoft has these amazing boards that are driven by Power BI that looks at the performance of various versions over time. And this, you'll probably go cross-eyed trying to read this all at once. But effectively what you're seeing in there is there's a lot of different places, these green cells, where .NET Core 3 is usually around 8 to 10% better on a lot of these things. Some of them are up 28%, 3.9. Some of them have regressed, and I assume that that's work that the team have still got to do before they go RTM to ensure that we're not regressing here. But that continual focused effort on performance in .NET Core has us at Raygun really excited about the future for .NET. So that's cool. The future is bright and incredibly fast, which is neat. We'd like to really thank you very much for coming along, especially those of you who stayed when we ran a little bit over here. It's been fantastic. You can find me on Twitter as TraskJD. Matt doesn't use Twitter because, doesn't waste time like I do. And there's Raygun.io on Twitter. We would also love you to check out our APM product for .NET if you want to have a look at performance on there. And here is the links. Again, we'll post these slides online. I just wanted to show this, though, for people who might be watching it online and just wanting to be able to type them out, which is pretty cool. So I thank you very much for that. I'll just check the Q&A box. And nobody asked anything. So we nailed everything they wanted to ask there, Matt. So that's awesome. Again, thank you very much then, folks. Really appreciate your time. And hope to see you on our next webinar. Bye.
See ya.